you all for coming out. We definitely appreciate this really nice turnout this evening. Before I introduce our guest speaker for the evening, I would just like to point out our final Science Cafe for the academic year will be held on Monday, April 22nd. That one will be at the usual time and location, so 5:30 p.m. at Cunningham's on the Bricks. And our speaker that evening will be Dr. Matthew Weiss from Kinesiology and Sports Science, and he's going to be talking about his research in health behavior training and intervention programs, especially as they relate to kind of public wellness. So if you have any interest in those particular topics, I would highly encourage you to come out. So that will be our final event of the year. This evening we have Dr. David Crouse with us. For those of you who are not longtime friends of his, I've been introduced to many of them over the past 2 days. Dr. Crouse originally came to us from Illinois. He received a bachelor in physics and then a master's in zoology in the late 1960s. He did a 2-year stint in the Army during Vietnam, and after returning, he rebooted his academic career and received a PhD in radiobiology from the University of Iowa in 1974. He did a 3-year postdoc in Chicago, after which he started his career at UNMC in Omaha. And over the course of approximately 35 years, he served in a number of different roles. First as a professor in the Department of Genetics, Cell Biology, and Anatomy, and then in a couple of administrative roles as the Associate Vice Chancellor for Academic Affairs, and then also the Executive Associate Dean for Graduate Studies. So I will let him take over. He's much more an expert on the topic, but he's going to talk with us this evening about all things related to stem cells.
Well, thanks for the invitation to come back to Kearney to talk even in this same area. Kim, you'll have to remind me when I was here last. It either was a lunch and learn or a science cafe maybe 10 years ago on this same topic.
Science Cafe.
Science Cafe? Yeah. I couldn't remember for sure. I've been here more than once. I've lectured in this room before as well as over at the Alumni House, so I'm going to lose track of where I've been and what I've talked about. But thanks for being here, even those of you who were mandated to be here. I know there's a small group of that ilk here. I hope that you enjoy it and you get something out of it. I try to aim this at an audience that might not have any particular interest in stem cells, yet have an interest in where things are happening in medicine and science. And that's where I'll kind of aim. I also want to welcome an old friend of mine over here. We were in the Vice Chancellor's seat for the same for quite a while, back in the 2010-ish or 9-ish or 8-ish or something like that. Because I served in that role as well, in the role, and we got to be good friends. The academic administration collegiality pool is not real big. You know, there's 4 campuses, so there's 4 vice chancellors. There's 4 chancellors, and now only 3. And it's an interesting way to learn about different campuses. And I learned an awful lot about UNK during my stint in administration, which was later in my career. So I feel like I know your campus fairly well. I haven't been here for 5 years doing something on campus, but I feel I know your campus well. It's a good campus. We get lots of good students from here at the Medical Center in all different disciplines. Some of you are going to be targeting us as a place to come for whatever it is, whether it's medicine, PT, or PA, or pharmacy, or nursing, or any of the allied health fields, which are many. And by the way, those are good, strong fields. We have a good group here on your campus that can take care of you here as well. So I encourage you to look at those fields. They're all good fields. Enough propaganda. So the day after I retired, I have been a member of the Coalition for Life-Saving Cures and Research Nebraska, which are a 501c3 and a C4 organization, for about 15 years. Since they started, I've been a member of those organizations. The first one, the Coalition for Life-Saving Cures, promotes primarily education, trying to keep people educated about research, particularly research that's important to the Medical Center and the other campuses, that keeps a vibrant research portfolio available to our faculty and to our students and to everybody else in terms of making advances in science. The other one, the Research Nebraska, is a C4, which means we can spend time walking the halls of the legislature, which I do, and talking to legislators about important legislation. This past year, we've talked to them a lot about smoking and how it wouldn't hurt to put a few cents or even a dollar on cigarettes to, one, decrease youth smoking, and two, put some money back into the important areas of research that have relied on smoking money in one way or another for a number of years. We all know property taxes are a big thing and Medicaid expansion is a big thing, but research is still important too. So I spend my time with public education and a little bit of, I'll call it lobbying for lack of a better word. So I'm going to tell you where I'm going before I go, and then you can go to sleep if you want to, or you can listen. All right, first of all, stem cells are not new. I'm going to take only one or two slides to show you that. Stem cells are not new. They're important normally for tissue homeostasis. All your tissues, almost all your tissues, need to maintain some kind of homeostasis. Most of them do it through a process of cell proliferation and replacement and replenishment. So you wear cells out and they get replaced naturally. That's a naturally occurring process, either by repair or just natural turnover. The definition of stem cells, which I won't get to till almost the middle of the talk, is real simple, but I want to go through some early stuff first. But not all stem cells are the same. It's one of the biggest problems we have with the public. They see a title in the newspaper that says, stem cells found to do this, and they think that there's just stem cells. It's much more complex than that. There's a myriad of different types, shapes, and sizes of stem cells. They're quite different. They're not the same at all. So I'll review some of those types with you, and what the differences are. Some stem cells are useful clinically now. If you know anything about our medical center, they've been doing bone marrow stem cell transplants since the mid-'80s. They're very good at it. They're one of the largest stem cell transplant, medical, hematopoietic bone marrow stem cell transplants in the nation. And they're doing some really cutting-edge therapy with bone marrow at the medical center. Something called CAR-T if you want to ask about it, or you can ask her, she knows about it too. So other stem cells may be clinically useful someday, and many of them are in clinical trials. And I'm going to talk a fair amount about embryonic stem cells and induced pluripotent stem cells, iPSC we call them for that. I'll get into that in more detail. Regardless, all these different types of stem cells, the standard ones like bone marrow, and the newer ones like embryonic stem cells and iPSC are really important in research. Even if we don't use some of them clinically, we're learning an enormous amount about cells, how they proliferate, how they're controlled. They're really basic biology being learned in great abundance. I'm going to talk a lot about some cautions I'll throw up your way about stem cell tourism. You don't have to be a tourist anymore to get these stem cell treatments. You can take your tourism right here in Kearney for stem cell tourism. You used to not be able to do some of this therapy that people are proposing without leaving the United States. And now you can get it right here in River City, okay, and Omaha. And it's not necessarily a good thing to do. And finally, I'll talk about the ethics in a lot of this stuff, time permitting. And I've got a lot more after that. If you want to push me, I've got some other things I can talk about. You might not want to do that, but I will. I'm going to start with the beginning. This always puzzled me. This is a slide, excuse me. This is a slide showing Prometheus and Zeus. And remember Prometheus? He's the demigod that gave man the ability to write, gave him fire. Remember Pandora's box? Well, he's the one that opened Pandora's box and caused all kinds of havoc. And Zeus was not happy about it. This guy, this is Zeus. He was not happy about it. Of course, this is all mythology. I know you know that. So Zeus decided to punish Prometheus. So Zeus tied Prometheus to a rock. This is not a rock here, but this is here, and this may be here. He tied him to a rock, and he called it what's called Zeus's eagle to come every night and pluck out his liver. He would pluck out his liver. It's an eagle. Pluck out his liver, and then the eagle would go away, and the next morning Prometheus was all better. His liver had regrown. I want to know how the people who generated this mythology more than 2,000 years ago knew that the liver is about the only solid organ in your body that regenerates even as an adult. I don't know how they knew that. I don't know if they did know that. It's just a good guess. But they hit on something then in the mythology that's turned out to be really important. We do now at the medical center, we do matched liver grafts, transplants, where a parental liver or a sibling liver can take half of it and put it in whoever needs the liver, and the half that was left in the person whose liver was taken as a donor, it regrows back to the same size. None of your other organs do that. Nothing. Nothing else can do that. So Prometheus and Zeus and the mythology that turned out to be right. But the science of it, people talk about cell theory. You probably talked about this in some of your early biology courses. Virchow was the one who said that all cells come from cells. He didn't say it in English, but he meant the same thing. And then another person in the German literature, Hacker, Stammenzella, stem cells. He was the first person to use stem cells. Didn't have anything to do with bone marrow stem cells or any of the stem cells we're talking about now, but he was the first person to use the term with respect to the meristym of plants, the growth tip of plants. And you knew that those were stem cells. And that's where they got the name. So the term's been around for a long time. We know that they're in many, many tissues, probably all tissues, but we haven't found them all yet. They're really important in skin and hair, GI tract, and blood cell. Some of us, unfortunately, I have mine, but there are plenty of guys, I see who this system fails, in males in particular, but in some females. It fails with time. And the stem cells that give rise to the hair follicle, in the follicle, quit producing, all right? And it's very hard to get them going. Minoxidil does a little bit, but it's very hard to get them going. But they're very important in wound healing, important in recovery from toxic damage. Those of you who might imbibe a little too much, the way your liver recovers after that insult is the stem cells produce new liver cells, and then liver regrowth. That's for surgery, which I already talked about. I see people looking at each other back there. There must have been some partying last week. Okay, practical example. This is an example we use with medical students. We actually have them do, we did, I don't know if they do it now. When I was there, we had them do this calculation. You can actually mathematically do this. I was a physics and math person. So you can actually mathematically do this. You know the volume of blood, or how many red cells in a cubic millimeter of blood, on average. You know what the average volume of a human being is in terms of how much blood volume. So you know how many total red cells there are. You know that the average lifespan of red cells is 120 days. That's been known for many, many years, but it's accurate. So you know how many cells are lost per day, and you can make one assumption in here, how many red cells are in each milligram of tissue, and therefore you're losing 100 grams a day, okay? And you destroy 90 pounds of red cells a year. So you're turning over, each of you, about 90 pounds of red cells a year. And fortunately don't retain them all, because you want to be red cell. But the same thing is true of your rest of your white cells, your granulocytes, your monocytes, not quite as much true. Your lymphocytes, not quite as much true. GI system is definitely true. You've got more of that shed. In fact, most of your fecal matter is those cells. It's not the stuff today. It's the cells in your shed and bacteria. Okay, so you need to have a strong recovery system, repair system, replacement system. And the best studied system is the hematopoietic system. It's blood, bone marrow, lymphoid forming cells. So I'm going to kind of review that a little bit. Why did that get so well studied? Well, we had a war. And after the war, we had a nuclear event during the war. This is World War II. And there was a lot of research that went into, we knew what killed the people in Japan, besides blast and fire and chemical and all those terrible things. We knew an awful lot of people died from radiation, but we didn't know how. And there wasn't a lot of detail on that. So the question was, particularly for our military, how could we protect or repair people who got exposed to a lot of radiation? So that was the original question in the late 40s. How can we protect our army, and how can we fix them if they get broken by radiation? So they knew that the neutrophil count drops precipitously after a good, healthy dose of radiation, but that would be lethal. It was pretty high. Your lymphocyte count goes down. In fact, this was actually used as a dosimeter, still is used as a dosimeter in some degree. It was used in Chernobyl. It was used in Fukushima by measuring the drop in lymphocyte count in the workers exposed. Good way for dosimetry, biological dosimetry. All these things drop, and then if you get a high enough dose, you get acute diarrhea, you get acute infection, drop in blood pressure, and you die within 3 to 15 days. Here, if you only have a lower dose, you'll die in a week or 2. Here you die in less than 2 weeks. Or if you get a really high dose, convulsions, unconsciousness, and you die in hours to a very few days. And we know that this is related to the dose. So this was known. Fortunately, very few people get exposed to these kinds of high doses, or extremely high doses. This is way higher, way higher than anything you see clinically, except for patients who are intentionally exposed to this dose, a high dose, about what we call 1 gray, enough to kill all their hematopoietic cells, but not kill their GI system. It's one way you prepare a bone marrow transplant patient to receive fresh bone marrow. You've got to make space for it. So you give them a real high dose of radiation, and then rescue them with bone marrow. It's called a rescue transplant. Right? So that's done routinely. There's no rescue from this or this. You get above this level, I'm not putting numbers in because you won't remember many of them, but if you go above this, you're dead. It's just a matter of when. There's no way to fix it. Well, how was this known? Excuse me, go back one. They established pretty quickly that spleen or bone marrow transplants could save animals, and that quickly got translated into people in the early 50s with the very first bone marrow transplants. They weren't very successful because we didn't know a lot about histocompatibility and genetics and matching, and a lot of people die from nasty disease that can't occur if you don't have matched products. But these were studies in the 50s, a long time ago, 50s, 60s. And the question was, we put bone marrow, or in the case of a mouse, spleen cells into an animal and rescue them, but is it the cells that are rescuing them, or is it the humoral factors, chemicals that the cells are producing? It took them a while to figure that out. And when they did, then they had to figure out, well, is it one kind of cell that does everything, makes all the different kinds of cells that are in the blood and bone marrow? Are there different progenitors? And we're just transplanting a bunch of cells, so we're getting some of each. I won't go through the details because it really is a little complex, but they showed pretty much that in the bone marrow system, there are stem cells that can give rise to everything, from lymphocytes to granulocytes to monocytes to red cells to platelets, the whole bit. All one kind of stem cell can give rise to them all. A little more complex than that, because there are then progenitors that are one step down the line. So you have the stem cell, which gives rise to a progenitor, which can give rise to less. Maybe only one kind of cell. You've got to realize there are different kinds of granulocytes. There are different kinds of lymphocytes. So you have one progenitor for multiple cell types. We'll talk more about that. That has gotten more advanced with time. We used to all do it by simply biological descriptive data. Now we've got all this molecular biology and markers and stuff like that, so it just blows your mind with the acronyms. But there's all these different markers, so we can show the same kind. It did not change the outcome in terms of what we know about it, but it did change the detail. We know a lot more about progenitors and stem cells. Lots of pretty diagrams that show how all these different cell types arise. We've also learned that there are other cell types in the bone marrow that also produce other kinds of cells that are important in the bone marrow and stroma. So they produce adipocytes, they produce various other kinds of stroma, and those are also important. These are sometimes called mesenchymal stem cells that produce this stuff here. They're also important, increasing importance. I'll come back to that. So bone marrow transplantation, big deal. Leukemias, lymphomas, some other genetic diseases, blood diseases are very successfully treated with bone marrow transplants. Or now, in my research area, blood stem cell transplants. So most of it's done with blood now rather than bone marrow, because we know how to get stem cells out of blood. There's still problems with other adult tissues, not the bone marrow so much, but other. The cells in most tissues are pretty rare. They're not very common. They're hard to identify. They don't grow well. They generally can only make one cell type, and that's the kind they're going to destined to be part of, the tissue they're destined to be part of. Most of them pluripotent, I'll come to that in a minute, pluripotent. The ability to make everything is not confirmed. And therefore, bone marrow is not a cure for Parkinson's and diabetes and Alzheimer's and spinal cord injury and COPD and impotence and everything else, as some people would like you to believe. Okay? There are people who are treating everything from knee injuries to COPD to spinal cord injury with bone marrow stem cells. To me as a stem cell biologist, that makes no sense at all. None at all. But it's gotten out there in the world, and it's pretty common. You find it. Well, this area became a publisher's playground. This is basic science journals. There's an equal number of clinical journals, blood, transplantation, a whole bunch of them that relate to the specifics of blood and bone marrow primarily. So hematopoietic cells are really well known, really well understood. And then in the early 2000s, National Academy of Sciences, National Research Council came up with this book, which is called Stem Cells, The Future of Regenerative Medicine. They broadened it a little bit and said, you know, we should start thinking more about stem cells generically rather than just about bone marrow. So the concept of stem cells really did get broadened into other areas. And now I'm going to define what a stem cell is. I want you to see the background before I give this to you. All right? First of all, stem cells can do three things. Some people say two, I say three. They can self-renew, they can replace themselves. So one stem cell can make two stem cells. They can differentiate, so one stem cell can make different kinds of cells. And they, in the process of doing A and B, they amplify, they expand cell number. The stem cell can also produce one daughter progeny that is different, that is differentiating, and one daughter progeny that's another stem cell. So they can do something called alpha division. So there's different names here. So they do this. They divide like that. All right? The next thing they do is we'll differentiate, and then they expand. All right? So that's the process. Self-renewal, differentiation, amplification. They do that. That's a good question.
I wrote down.
Okay. Stem cells are also clonogenic. That means they're one cell, and you can track the chromosomal markers of it. You can track it back from the progeny, it goes back to one parent cell. They're very hard in all systems to identify by the way they look or where they're found. Sometimes they're in specific locations, sometimes they're not. And this reproductive integrity has to last for a long time. If you're going to be 95 and still producing 90 pounds of red cells a year, think how many red cells you produced over your lifetime. Tons, literally tons of red cells. Okay, so it's a remarkable, stem cells to me are remarkable by what they can do. They have huge potential, which is one reason the public has gotten kind of sold on it. So we've talked about that. But we have stem cells in the skin. Replace your skin every few days. In your GI system, they replace your GI system, recover your re-epithelialize your GI system every few days or a week or two. Your liver does the same thing, and so on and so on. We even know now that some neuronal cells can be replaced by naturally occurring stem cells in the brain. For a long time, we taught the medical students there's no replacement in the brain. When you lose that neuron, it's gone. So after the age of about 18, you're going down. Okay, I'm way down. But that's what I talked about mostly. But it's much more complex than that. This is kind of the traditional view of how this works. There's only one total, everything, totally potent stem cell. That's the first day of fertilized egg. That's the only one that can make everything, can make all the cells. Your neuronal tissues, your GI, everything. It all comes from that one cell. You've got to realize that, or you wouldn't be here. Pluripotent cells are those in the early embryo. About 5 days into the embryo, you have pluripotent cells in that just beginning to form embryo. Remember when you get a blastocyst, I'll show you pictures in a minute. There's the embryo, which is called the inner cell mass, is the beginning of the embryo, and then you have the trophoblast out around it. Well, those cells are not pluripotent. Only the cells in the inner cell mass are pluripotent. These pluripotent cells then give rise to multipotent cells. So the stem cells of bone marrow, which I spent a long time talking about, are not pluripotent stem cells. They're multipotent stem cells. They give rise to everything in the hematopoietic blood-forming, lymphoid-forming system. But they don't give rise to nerve cells. They don't give rise to liver cells. They're not island cells in your pancreas. Same thing's true for other systems. These have ultimately come down to unipotent cells, so that some cells can only make lymphocytes, some cells can only make red cells, or platelets, or granule cells. This red box is what you have in the adult. All your stem cells belong in that red box. Every one of them you've got is in that red box. They're not back here, as far as we know. Although some people claim that they're somewhere. The evidence is very strong. Well, partly because they're not well understood, and people started touting things about them, it literally became a minefield. People talk about stem cells in the public literature, in the domain out there in the press, without being specific about where they came from or what they're doing. And that can be really misleading. That's been going on a long time. But why is it important? Well, we know that a lot of incurable diseases result from either damaged or dying or non-functional cells, whether it's paralysis or heart attack or diabetes or all kinds of neurodegenerative diseases. You've got dead, dying, or non-functional cells in those tissues. And the idea is if you could find a progenitor or a stem cell that could become that cell type that you're missing or non-functional, then you could cure that disease. So the idea was that this could happen. You could find stem cells, push them through to become what you want them to become, and cure these cells. You don't transplant the stem cells in any of these situations. You have to drive them first in culture or some system. You've got to drive them close to their destination so they can function when you get there. So if you take stem cells from a total pluripotent source, you need to drive it down the line of neuronal cells or nerve cells to get them to replace or fix paralysis. Or a heart attack, you need to drive them towards cardiac cells. You can't transplant the stem cell. You've got to get them close to what you want them to be, or that you're actually going to get problems. So that is the basis for hope, is that if we can find out how to take pluripotent stem cells and drive them in the right direction and know how to control them, we would be able to treat a lot of diseases. So that brings embryonic stem cells. This became an immediate furor in the literature. Embryonic stem cells are not new. They go back to 81. It was in 96 that Jamie Thompson described them in primates, and then 98 that he developed pluripotent stem cells from inner cell mass embryos in humans. Right? That lit a spark of controversy. Well, why did it light the spark of controversy? Well, here you got a fertilized egg dividing to 2 to 4 to 8. This is the embryo at 5 to 7 days. This is the inner cell mass. This is the trophoblast. This becomes the placenta. This becomes the embryo, later fetus. This is just 5 to 7 days. This is not implanted yet. In fact, if you know people who have gone through in vitro fertilization, this is what the in vitro fertilization clinic is working on, something along about that stage. They're working with that pre-implantation, very, very, very early embryo. That's what gets put into the woman who's trying to accept it in an IVF procedure. Okay. Size-wise, this is the morula, 8 or 16 cell stage. This is a dime. This is the blastocyst. This is the eyeball of good old Mr. Roosevelt. They're pretty small, almost invisible. So here's the hypothesis. Remember, this is a pluripotent stem cell. By definition, the inner cell mass can give rise to the entire embryo, all cell types. So by definition, if we took a leftover embryo, all embryonic stem cells that are used clinically, or right now in clinical trials, or experimentally, are derived from leftover embryos destined to be destroyed. That's where they come from. I'll get more into the ethics of that later. So you take the inner cell mass, disperse these cells, and that destroys this embryo. That's pretty obvious. Put them in culture, treat them right. They can become pancreatic cells, or heart muscle cells, or blood cells, or nerve cells, or bone marrow cells, anything you want. If you drive them toward the nerve cells and make them dopaminergic nerve cells, theoretically, you can treat Parkinson's. Okay? And indeed, in animals, rats and mice, that's been done. So this pathway, here to here to successful treatment of animal model organisms has been done. As has been done with, by the way, as has been done with a number of others. It's been done for diabetes, it's been done for spinal cord injury. Those are all successful in animal models. I'll come back to that. So this is a culture of myocytes, human myocytes, that are driven from human embryonic stem cells. I'm not sure if I do this with this. Let me find my marker here. When you drive them to cardiac myocytes, they pick up a natural rhythm. They beat. So not only can you clinically, morphologically say that they're cardiac cells, they beat with a natural rhythm. And they do transplant, and they work in animals. So we know that works in animals. This, I didn't have any luck getting this to run before. I was going to show you that even in the inner cell mass, you may only have 30 to 50 cells. Those cells have their fate determined very early as to what they're going to do. Even in that tiny ball of cells, some of those cells will get it early enough before it actually forms a blastocyst. A small group of those dividing cells will produce the trophoblast, and others produce different areas of the embryo. They aren't all pluripotent. So we know that although they're fairly pluripotent, they may be limited somewhat in their wide range of what they can do, which is actually causing some issues in stem cell biology. So, where do we get human embryonic stem cells? Excess of IVF, no longer needed for reproduction. There are enormous numbers of these. There aren't any newer numbers than this survey done in 2003. Only a small number, less than 3%, have been used for research. Very small numbers. This number's outdated also. Lots and lots of cycles of IVF. This is becoming incredibly important, especially as the female population ages. The choice of having kids gets moved later and later. More and more of them are choosing IVF also. They estimate they're accumulating 50,000 a year. If you believe that, this number is off by a factor of a third. I mean, it's 3 times that. How long do these frozen IVF products last? We really don't know. We know that in the meat market, animal market, many years, 20 years, 30 years, they're fine. No problems. So experimentally in animals, they're many, many years. The oldest IVF embryos used in people are about 15 years storage. So how old's that kid? Produced years ago. And they're born now. A 15-year-old birth. That gets ethics problems that I don't mess with. All right. The big key here is these are destined for destruction as medical waste. IVF embryos can go a lot of different directions, including adoption, including other kinds of technical uses for training within the IVF laboratory. They do use some for training, not for research, and that has been going on for years. You have to have informed consent. Extensive detail is required. There could be no financial inducement. You have to separate the person who's using the embryos from the person who collects the embryos. They have to be completely separated. Again, no relationship. Most parents who have embryos being stored select research. These are all different kinds of research, but research is the main thing. If you select cloning, not many of them want to donate the embryos for adoption, because a lot of people don't want their genome running around without knowing where it is, and that's the bottom line. They have no desire to have unknown children out there, which might be tracked. If you watch these Roots type shows that are on TV, you'll know that a lot of people go back and find parents that they have no idea who their parents were. You do it now. Should stem cells be used for this kind of research? The overwhelming majority of the public also says yes. The question I always get asked is, so when are embryonic stem cells going to be used? They were discovered in '98, almost 20 years ago. All right, so when are we going to use them? A little story here. Stem cells for blood production were first discovered, as I said earlier, in the late 40s, early 50s. First successful uses of these, with lots of failures between here and there, was the late 60s. And widespread clinical use wasn't until the 80s. And the time here, pretty easy to get out to 20 or 30 years. It's easy to get to 20 or 30 years. This is a simpler system. Okay? So how long is it going to take for embryonic stem cells? 98 to Clinical trials, which have been initiated in the past 4 or 5 years, there are a lot of clinical trials going on in the United States and elsewhere using embryonic stem cell products. No widespread clinical use yet. The ongoing trials are spinal injury, blindness, macular degeneration mostly, diabetes, and cardiac. Those are the main areas that we looked at for embryonic stem cells. We don't know if they're ever going to pan out. A lot of people claim initially, including some scientists, stem cells are going to cure all diseases. That's hype. That probably was never true, and it caused confusion in the public. And a lot of irritation when it didn't pan out quickly. So it may or may not get there, and we're always bound up by these clinical issues that are ethically based. And I'll come back to that. I'm not going to leave that, just not now. So here's the current clinical areas. There's references here. I'm leaving this PowerPoint up here if anybody wants to chase these for a paper or anything like that you might be pursuing. So we're left with your faculty here. But you can see these are all 2014. All those clinical trials are still going on. So clinical trials, most people don't understand, take a long time. They don't happen very quickly. They can take a long time. So the hope here is that embryonic stem cells may lead to treatments or at least understanding of diseases in the next several years. The hype was that this is going to fix everything. That hype is not true. Other approaches. I'm going to just breeze through this. Somatic cell nuclear transfers, also called cloning, or therapeutic cloning to be more precise. It's been done with humans now. Here the process is different. You don't need an embryo, you make one. So you start with a donor egg, any female donor egg, human works, and you take an adult somatic cell, most commonly skin, just scrape a little bit of skin off, take a biopsy, take some nuclei from these cells, put one nucleus in one egg, and drive it chemically and with some shock treatments to become an embryo. This nucleus that is implanted there is a diploid nucleus. It has the chromosomal complement of the donor here. Okay, so it's going to look like that donor. It's compatibility. It'll look like that donor. And this embryo is going to be basically that person, quote unquote, clone. The idea is to take these cells, plate them, get pluripotent embryonic stem cells, and do the same thing you could do with embryonic stem cells. The controversy is because you could also implant this, as Dolly was done in the sheep, and lots of other cloned animals now. In fact, almost every species but man has been cloned. Major species. So dogs, cats, sheep, cattle, goats, pigs, you name it, they've all been cloned. In fact, they're not uncommon in the husbandry industry. But nobody wants that to happen in people. I still think someplace, somewhere, just like the renegade who just produced genetically manipulated babies in China, somewhere, sometime, there will be a renegade who's going to do that. The technology's there. It's just going to take somebody breaking all kinds of ethical principles to do it. I'm sure we have headlines. These are convenient cells to have because we can study all kinds of things, and you might be able to get your own compatible donor for almost any disease you have. You can make your own pancreatic cells, your own liver cells. They would not be rejected. But this is kind of fallen by the wayside. A lot of people, it's got a huge amount of controversy. All forms of cloning are unethical because they have the chance of branching off into reproductive cloning. But it's still, in terms of technicality and what you can get from it scientifically, it's very interesting. It has great potential. It's almost stopped. There's just a few places who are doing SCNT work at all. It's not allowed with federal money in the United States. So let's do it some other way. Fortunately, we have some really talented colleagues around the world. This was the headlines in Science in 2008. I had to attend Dr. Yamanaka's lecture in Toronto at the International Society for Stem Cells meeting when he presented this before it was published. What he did was he produced induced pluripotent stem cells, iPSC. This technology is moving so fast that I can't keep up with it. I'm familiar with the area, but it's just raging along. They all start with adult cells, usually with skin cells, or now with lymphocytes and some other cells, and you directly convert them to a phenotype that looks like an embryonic stem cell. Originally, it was done with viruses. And Dr. Crouse can tell you all about this kind of stuff. This is an area she worked closely with. But this kind of stuff is dangerous to do this, because you can carry over things that you don't want to be transmitted. You have the potential for doing it. But that was the first way they did it. They added 4 genes using a viral vector. Yamanaka did that, and Jamie Thompson did it with 4 different genes in Wisconsin. And about the same time, they did the same thing. All right, so you call these iPSC. Starts with normal cells. You don't need an egg. There's actually no controversy regarding this, regarding the ethics of it. What's controversy? None regarding the ethics of it. You get genetically identical cells that match the donor. You don't even have the mitochondria from that donated egg that you get in SNT, which gives you a little bit of DNA difference. You don't get that here. This is all going to be used. Quite a thing. No use of embryos. This signal thing has gotten way beyond that. It can be used with gene therapy and all kinds of things. So it's quite the system. So Japan has gone gangbusters in this area. They are, iPS stem cells are us. That's them. They are the only ones doing widespread iPS therapy. They started out autologous, which means from the same person, and they learned pretty quickly that when you make these stem cells, they have almost a blank slate phenotype in terms of the immune response. So they started using allogeneic, which meant they could build lines, bank the lines, and then take cells from the lines and quickly transplant somebody for all kinds of diseases, retinal diseases, heart diseases, Parkinson's, cornea, spinal cord injury. All these are ongoing trials, and they're all really pretty recent. This one was just last week. So it's moving so fast, and the clinical results right now are pretty good. They have not had any what we call adverse events yet. It's early yet, they haven't had any adverse events. They're way ahead of us in this country, way ahead. One further step than iPSC, well, how can you get simpler than that? Well, why not just directly convert fibroblasts? We know what these genes are producing, what the gene products are. Why not just put in gene products instead of genes? So let's throw the gene products in. So you take normal stem cell renewal does that. This is the way you get your normal products of cells. Here's your fibroblast. That comes from a stem cell too, just like everything else. All right. And if we do an iPS cell, we take this fibroblast, genetically manipulate with viruses or something, put genes in it that drives it back to here so we can make a neuron or whatever we want. Direct conversion takes the fibroblast, takes the factors that you would get from these genes and directly converts them to what you want. That's actually been fairly successful. Not widespread yet, but fairly successful. So, stem cells, fiction was that stem cells are the same regardless of source. I hope you understand now stem cells can be very, very different. I've talked about a lot of different sources. Adult stem cells and embryonic stem cells are by no means interchangeable. They're completely different from each other, and they're remarkably different. So what did this cause? A lot of the stem cell work, which sometimes only superficially makes it into the press, caused a lot of hype. And 15 years ago, the hype caused people to get on airplanes and go to the Philippines or go to China or go anywhere else in the country, this country, and get a stem cell transplant for whatever ails you. And I do mean whatever ails you. You may have a death-producing disease. You may have autism. You may have Alzheimer's. You may have impotence. They didn't care. They would treat anything. So this went on. But there are also now harmless things that got produced from this. So you could go on Amazon. I wanted to see what the latest products were. So I went on Amazon last week. These were all pulled off last week. These are different stem cell products. I just searched stem cell therapy. And I just picked the drugs. And these are just the I'll call it cosmetic drugs. And here we have one for acne. So if you've got bad acne, you put some stem cell stuff on your face. Fix it. If you want to live forever, over 100 years, they've got a prep. You can even mix it in coffee if you read the fine print. Salves that rejuvenate your skin, bring it back to that youthful appearance. Most of you don't need that yet, but some of us do. Serums, they call them, same things, basically.
Stem cells.
And Apple, I don't think it has any connection with it. They got away with it, so they're using that. But for the more dangerous ones, some of them are potentially harmful, and they're being stopped in many countries. This is old data. That doesn't mean it isn't still going on. Where these companies in different places in the world were treating all these different diseases, and this is what they charged you. Some of them have been suspended. I suspect more of these have been suspended. And fewer of them are getting American patients because you can now get it done in the United States. You don't need to go to Beijing. You get it done right here in the U.S. Okay, so there's a good paper that came out if you want to read it. This is in the open literature part of Cell Stem Cell. It's one of the cell journals, just a couple years ago, 3 years ago now, called Selling Stem Cells in the USA, Assessing the Direct-to-Consumer Industry. And this is for unapproved, FDA unapproved, no clinical trials, therapies that are being offered in the United States. They don't have Kearney on here, but they do have all. You were right there. And I know that the clinics that opened out here came just after this paper was published. And I told Paul Knopfler, the guy who wrote the paper, you need to redo this map because we got several up in Nebraska, Omaha, and Lincoln, and Kearney, not just Omaha. But you can see they're where the old and crazy people. I include that, so that's where they kind of live. These were full-page ads in the Omaha World Herald. They've run them twice over a period of about 5 days. I only put 3 on them because they get so small here. But they did it over a period of 5 days, and they repeated them about 2 weeks later. They're advertising workshops, which I attended, for neuropathy, COPD, back pain. They have one for arthritis. I forgot what the other one was. All at the same number. Well, actually, it's different numbers, so because they're different nights they did the workshops. The second round, they were offering dinners, kind of like what they did here in Kearney. These are Kearney. Some of you may have gotten these in your mail. These are great big postcards that came in the mailbox, offering these things here in Kearney. Schrock is the name of the chiropractor. By the way, a lot of these programs are offered by chiropractors and non-physicians and nurse practitioners. Lots of people do this. None of it is FDA approved. Most of it has minimal scientific basis. Sometimes there's hints of scientific basis, but it's really minimal. The people that say this works, it's all testimonials. So if you're a scientist, testimonials at work don't. The bad thing is some of these can be very dangerous. And there are increasing reports of what we call adverse events. So people going blind, people dying, these people die, people having serious tumors as a result of these stem cell transplants. Nasty things happen. Just recently, and I didn't add it because I didn't have room on the slide, I didn't want to add another one. A company in California that produced stem cell products that got distributed around the nation. Turns out their product line was contaminated, and they were contaminated with what's something really nasty, E. coli. That's a fecal contaminant that was in the stem cell products. And all kinds of patients got E. coli infections from stem cell products. So you go in for one of these, just beware. There are side effects. Most of the time, they're not going to be fatal. These are a little bit rare, but they did happen. The FDA has warned about stem cell therapies. This is right from the FDA, not that long ago, a year and a half ago, almost 2 years ago. Stem cells have been called everything from cure-all to miracle treatments. Don't believe the hype. That's the bottom line. If you want to take another thing away from here, besides what are the characteristics of stem cells, don't believe the hype. They've gotten more serious about it in that they're sending warning letters, suing, and cease and desist orders to some of these companies just in the past year. We're all concerned that the FDA chairman Gottlieb just left, resigned. So there's going to be a new chairman of the FDA. We hope that person puts as much emphasis on as Gottlieb did, because it's important to keep the pressure on these clinics and these fly-by-night operations. Many of them are fly-by-night. So this is putting them on notice. You can go on the FDA website, there's all kinds of stuff. They actually have the letters of warning, what they found when they inspected the labs and the clinics. They found all these contaminated equipment. It's just disgusting when you read what they found and why they're cease and desist. There's a handbook available from the International Society for Stem Cell Research on patient therapy, or patients to beware what to beware of. Their website, just at ISSCRE, is a real simple website, and then you look at their page for patients. So the fact versus fiction here is the fiction is stem cells from many sources can develop into all the most needed cells we need for therapy. We really don't know. The data supporting use of adult stem cells is controversial at best. We know that bone marrow works after 50 years. We know it works. But for most of the others, it doesn't. I'm going to take 5 more minutes to do something about the ethics and politics, and then I'll let you ask questions. Okay. Well, they really became a big cartoon topic. Embryo-thaw, blastocyst harvester, stem cell waster, research Luddite. At least it's nice to get past babyhood. We've actually had some of our physicians in medical centers who supported the research that we've done in medical centers. They weren't even doing it. They just supported the fact that it was being done. They have actually been called in emails and public letters baby boomers. To me, that's pretty offensive. But I'll tell you a secret. Some of the cartoons are right to the point. I love this one, actually. Cartoons on, I died waiting for an embryonic stem cell research to find a cure. What about you? I was the embryo. Puts it right where it is. That's the bottom line. The core argument for those people who are interested in maintaining an open research environment that allows stem cell research to include embryonic stem cells, bottom line is these cells are going to be destroyed, and therefore they're being saved from that embryo for potential clinical use and research. We may actually find some very good things come out. Otherwise, they're going, for the most part, 70% of the patients have been destroyed if they don't go for research. The opposite is an embryo is destroyed. Bottom line, that's true. There's no way you conduct that. The embryo is destroyed. If you take the philosophical, humanist opinion, religious or otherwise, that embryo, even from the 1 or 2 cell stage, is a person to be, then that person is destroyed. No question. You can't argue. A scientist cannot argue that point. That's true. You have to make a decision based on some evidence. We say in Crouse that this fulfills an ethical obligation to alleviate human suffering. This is part of the Hippocratic Oath, to alleviate human suffering. If this is a way we can do it, it's ethically stable to be able to do that. Since basically most of these are going to be thrown away anyway, isn't it better that they've used in research than be trashed? And literally, they were trashed. They were put on a blue diaper, as we call them in the lab, allowed to evaporate, then thrown into biological waste for incineration. That's what happened to them if they weren't used. And this in vitro product has never been in a person, except the actual egg, sperm. And they are microscopic. They have no differentiated tissues in them, and that does not meet the definition of person. That, by the way, it doesn't meet the federal definition of person either. But those who are against it, it doesn't matter. Nothing justifies the destruction of an embryo. It is murder. And I have been on daises with people who take the opinion opposite of myself. I cannot say they're wrong. I cannot, as a scientist, say, you're wrong. That is a tough one. You have to weigh all the stuff. You have to think long and hard about it. They say there's also a risk of commercial exploitation for people who do embryonic stem cell research, or at least the participants in it. The risk, I think, is small, but there may be some risk there. And they use a slippery slope, but eventually we're going to be reproductive cloning and all kinds of other things. I think that's even more now. The one you can't dump is this first one. You cannot dump that. Okay, we had 20 years of hope and controversy. It's beginning to move into the clinic. This is just this year, last year now, about a year ago, that Science had another big review of it. So, the fact versus fiction here. The fiction is the ethical differences between embryonic stem cells and stem cells is black and white. I contend it's not black and white. It's lots of shades of gray. It's not simple. And you base your decision based on a lot of things. The science, your background, your religion, your own moral position on it, and all that blends in, and it blends in differently for different people. So you have to make the call. If you're doing embryonic stem cell research, you have to realize what you're doing. You wouldn't dare do it without knowing what you're doing. You have to know what you're doing. Okay, we don't know everything about stem cells, particularly how they function. We've learned an enormous amount from all these different kinds of stem cells. And we do know they're not the same. So it's fascinating to me as a scientist to see how different they are and what the potentials are. The ethical issues are complex and I hope manageable down the road. New cell lines are being available, whether they're IPS or embryonic, all the time, and they will advance our standing. Some of them may lead to therapy, some of them are leading to therapies. This is going to go forward, this is a big point, with or without us in the United States. The United States has dropped IPS research almost completely. It's not going on greatly. Japan is so far ahead of us, we best get on track shoes if we want to catch them in their IPS cells. Embryonic stem cell research is big in a number of other countries already. The United States had it banned for so long, still is not allowed federally with federal dollars, but we lag. We lag a lot of countries in that area. Height has caused all kinds of problems in terms of stem cell clinics and what they're doing and what they can't do. And I could show you a bunch of more stuff on that, but here's where I've got a break point. I've got about 55 minutes about, so I've got a break point, and I can either talk a little bit more about political and legal stuff, or maybe let you ask questions and then decide whether we want to move further. Actually, I have a lot more slides. I can keep it till 9 o'clock. So I won't do that, but I could. So please, questions. I'll be happy to respond as best I can. I know it's By the way, I did not do it during some sort of research. I did something more dramatically controversial, and that's fetal cell research. Okay? Can't know that. All my work was with mice, some with dogs, but mice mostly. But the idea was to model what's going on. That is incredible. I didn't talk about it. Although it was twice down the stack or something. So, any questions? We have to respond. Anyone want to go for politics? That won't take 5 minutes.
I do have a question about that.
Sure.
Where are we in the state of Nebraska with trying to regulate some of these places that are doing the stem cell therapy?
We have asked, we even said we are a coalition, has asked the medical moms, Metro Omaha Medical Society, to intervene if they can. It's very difficult to get physicians to regulate themselves. Very difficult. And that's true in all areas. One physician knows that this doc down the hallway is doing drugs, and they've been on for years. It's really difficult to get docs to regulate themselves. And so they have not been willing at this time to take up the ban. The thing that's kind of, I think, caught their interest is the guy out here is a chiropractor. They don't like people stepping on their turf. Okay, so that's another thing that kind of might get them interested. In Omaha, the clinics do have an MD who is over them, although the actual clinic sites, there's 2 of them, are run by nurse practitioners who actually do the stem cell administration. They do the physical and everything. So the physician who's over it isn't even in Nebraska, but he's licensed. Yeah.
What's the source of the cells being injected?
They vary hugely. Everything from umbilical cord to adult bone marrow, to your own bone marrow, to amniotic fluid, to mesenchymal stem cells derived from other tissues. Some is even cadaveric for bodies. So it's a huge range of different donors. The one that got contaminated with E. coli was umbilical cord cells. Came from they've been shut down after probably not Christmas.
Why is it so easy to get stem cells?
Why is it so easy to get them? Because most of these people aren't getting stem cells. They call them stem cells here. It's been some laboratories in this country have bought the stem cell products and checked them for stem cell activity. Some of them, there's not even any cells in them. There's not even any cells, no living cells. there's debris. Some of them do have some stem cells, but they're uncharacterized. So they call them stem cell preparations because they got them out of the bone marrow or fluid. They say we have a stem cell prep, sometimes just for your blood. And we're going to inject you with the stem cell prep in your knee, in your back, in your shoulder. Those are the most common. Those are also the least likely to cause harm. So it's a little harder to get physicians to jump on people who are not likely to cause harm. The only harm they can cause you is right here, in pocketbook. $3,000 to $5,000 or $6,000 for single treatment. The talk I went to said they rarely do single treatments because they're not really that successful. They admit that, and you need to have 3 to 5. I mean, more the better. So you can spend $15,000 or $20,000 for here in Kearney, I understand 6 or something like that for a single treatment.
Yep.
And they also encourage, I assume, more than one treatment. So it's disgusting. But the FDA is slowly doing something. But they're underpowered, under-manpowered, and underfunded. Really good.
So if put these cells in, and like you said, some of these others, you have to, if you had them from regular cultures, you have to drive them in some ways to be.
They don't do anything.
No driving,
No.
no driving.
They're just assuming, what they will tell you, and the guy said this, because the patient asked the question, well, how do these cells know what to do when you inject them? And his response was, well, that's what stem cells are all about. They know what they're supposed to become. And they recognize the environment they're in, and that's what they become. Ooh. I'm sorry, but that would be my response. There's no scientific validity to that response, to that answer. None. Most of these people wouldn't know a stem cell had been, frankly, stem cells don't make. Don't get me on soapboxes. I get a little, are there any chiropractors in the room? You should be careful. But it's true. I'm not saying anything that I could be sued for, I assure you. That they would have a hard time showing that I have said anything false. Very hard time. So, yes, ma'am.
What kind of things have been done or are being done to educate the general public about?
Well, I will talk anywhere you give me a soapbox. So I have been all over the state, mostly Omaha, Lincoln, doing science cafes, lunch and learns. We bring in speakers to the medical center as often as we can. We, as the coalition, we firmly believe that we need to start with you all, or even younger, in terms of science education, so that you understand science is based on facts. There's a horrible battle going on right now with science facts. There are people who don't believe that facts are facts and think that there's other things besides facts, other things besides truth. And it's to the scientist, it's really discouraging when people won't listen to the world's authorities in different areas, whether it be climate science or environmental stuff or medical scientists or what have you, and they say, oh, it's all biased. It's all set up by industry. Industry's controlling all that. I'm sorry. Good science is driven by data that's seen by the other scientists and reviewed by other scientists, and passes through that peer process, a tough peer process, by the way, for when it gets published. Then I would believe that before I would believe a personal testimony. Personal testimonies are just that. People will say what they believe. The placebo effect is really strong. There are a couple of papers that show that the more money you spend, the stronger the placebo effect. I mean, they spent $15,000. You don't write a word. So it's maybe you should charge more. People get better faster. Any more questions? Just so you know, go ahead.
Well, I have a question about your part of your early career when you're talking about studying radiation.
Yeah.
And after World War II.
I wasn't that far back.
I know, well, this is a question. I've never found anyone who has heard of this before. So my father would be 102 this year. Well, he had shingles as a young person and treated with radiation. Have you ever heard of that treatment?
Oh, they treated all kinds of things with radiation. In the late 40s, early 50s.
Right, that's the time period.
Terrible things happened to some of those people who were treated. And some of the things we didn't know. I mean, I could go on with a whole bunch of them, but one of the things that was commonly treated, they used to think that the thymus of a young child, 2, 3, 4 years old, they didn't see a shadow on X-rays. They were taking X-rays back then. It wasn't very high quality. But they could see the shadow of this thymus, and they knew that in adults it wasn't that big a thymus. So surely that thymus is infected or aberrant, going to be a tumor. Hundreds and hundreds of kids received chest and neck radiation. Thousands of kids received chest and neck radiation to reduce the size of the thymus. It did. And then 30 years later, they got thyroid cancer. Very common. So there have been a lot of things like that. It's been used for baldness, to cure baldness. It doesn't, they can give them a sunburn, but it don't cure the baldness. Radium dial painters, the women, most of the women, almost all women, young women, who painted the dials on old watches that used radium to produce the glow at night. They would tip paintbrushes with the tongue to get a fine tip off, paint those little handles, and dip it in the radium paint, and let it paint. Literally, 100% died of bone cancer. And that was, they were doing that through the 30s and 40s, having no idea that radium was toxic. So there's lots of stories like that. It wasn't until after World War II, all the national labs were built after World War II. All the national labs at that time, that's where I did my postdoc, was in Oregon. All the national labs focused on pulsar radiation stuff. And that's what I did, just like at Oak Ridge and Livermore and Berkeley. They all did the same kind of stuff. Where I did my work was late effects, the long-term effects of radiation. And I was particularly interested in high-energy radiation, neutrons and protons. That was just coming into vogue for therapy for patients. It still is. How different that is. As a physicist, I was fascinated by these particles. They sling around these electrons, huge energies. Get to a tumor right in the middle of the brain without damaging cells on the way in. Works. It does work. But there can be significant effects. Anything else in the area related? Let me stop there. Just want to see what was up there. I want to show you one thing here, and that's this. The stem cell compromise in Nebraska, this is Nebraska, was passed in 2008. This was a compromise, legislatively driven compromise to allow stem cell research per the federal guidelines. So you can do anything in Nebraska that's allowed by federal law with respect to embryonic stem cells in particular, but also other things, cloning, stuff like that. But the federal law doesn't allow cloning, so you can't do that in Nebraska. Federal law doesn't allow you to make embryonic stem cells, so you can't do that in Nebraska. But federal law does not allow you to destroy an embryo for stem cells, so that we can't do that in Nebraska. But we can use embryonic stem cells that have been approved, and as that area has expanded, there are a lot more. So it did get to the Board of Regents eventually. They came out. Were you there for that? You were there, Charlie. Were you
Yes.
there? I was there.
I remember.
As you recall, I was one of the people who spoke.
I do.
But this is the Regents took a shot at it. They didn't throw it out. So we're basically in 2019 the same place we were more than 10 years ago. Even with changes of administration and state and federal, it's unchanged in the state of Nebraska. Trump has chosen, at least so far, he's chosen not to tamper with the Obama changes in the Bush guidelines, which actually made them more strict in many ways. So he's decided not to tamper with them so far. I'm not saying he won't, he could. But for example, if the federal government decided to shut down embryonic stem cell research at the federal level, there would be a huge battle first of all, but if it was successful, then we would not be able to do any kind of research in Nebraska. That's the way the law works now. Nobody's taken this up in recent years in the legislature. It's been very, very quiet. So, yes, ma'am?
Was that legislation referring specifically to human embryos?
Yes. Oh, mice, and I guarantee you, with a vibrant agricultural community in Nebraska, they're doing some of this stuff. It's going on at the zoo. Zoo's very interested in being able to maintain endangered animals, and some of the endangered animal maintenance may come through some of these pathways that are not allowed with humans. Got a good reproductive biologist friend at the zoo. Anything else? And if you got a question that you're embarrassed or don't want to ask because you don't want everybody to stay, come on, talk. I'd be happy to answer. So thank you again.